Welcome back to this first lecture on the computational complexity of algorithms. We're going to conclude this lecture by analyzing the time complexity of a couple well-known algorithms. The first one is the binary search algorithm, which solved the following problem. Remember that this problem is slightly different from the one solved by linear search because in this case, the sequence of objects given an input is assumed to be sorted in ascending order. Here is a description of the input and output of the binary search algorithm, and here is its pseudocode description. Make sure you study it carefully to re-familiarize yourself with it before watching the rest of the video. So we're going to now study the time complexity of this algorithm, and remember that the first step always is to decide which primitive operations are going to count in the estimate of the runtime. So, what are the primitive operations in this algorithm? Well, it starts with a couple of assignments. Then there's a while loop, which itself is decomposed into comparisons, assignments, some arithmetic operations, and then there's an if statement made up of the same kind of operations. So clearly, this part of the algorithm will take constant time regardless of the size of the input sequence. Similarly, these two steps take constant time. So the runtime of this algorithm is dominated by the runtime of this while loop. In particular, the body of the while loop takes constant time. It takes an assignment statement, one comparison, and then one assignment statement, either this one or that one. So what we need to do is, or what we will do is to count the number of times the while loop gets executed. But for now, to determine the runtime of each iteration, we could, for example, choose as primitive operation the number of assignment statements. Notice we could also use the number of comparisons, but let's say we just pick the number of assignment statements, and I'll let you check at the end that you would get the same result if you picked the number of comparisons. So, the answer to this question is the assignment operations. So let's go ahead and compute the time complexity, the worst case time complexity of this algorithm, namely how many assignment statements are executed in the worst case for an input of size n. As usual, we'll call this number f of n. Now this number is equal to the sum of the number of assignments performed here, which is 2, plus the sum of the number of assignments performed during the while loop, which we're going to compute next, and then plus 0 because there are no assignments performed in this last step. So let's compute the number of assignments executed in the while loop. We already know that for each iteration of the loop, 2 assignments are going to be executed, one here and one of these. So the total number of assignments in the while loop is going to be 2 times the number of iterations in the while loop. So let's compute this final number. Remember that binary search operates by considering a subsequence of the whole sequence. Initially, the subsequence is equal to the whole sequence, and then every time through the loop, the length of the subsequence is cut in half. And the while loop terminates when the subsequence under consideration is of size 1 because L is equal to R. So in other words, the number of iterations of the while loop is the number that is equal to the number of times it takes to divide a sequence of length n by 2 until you reach a sequence of length 1. That number, by definition, is the logarithm base 2 of the length of the original sequence, that is, log base 2 of n. So here is the approximate expression of f of n. Now, we finally need to derive a big theta relationship for f of n. Well, we already know that 2 times log n is a function that's proportional to log n, so therefore this is big theta of log n. The constant 2 does not matter. And this constant is big theta of 1. According to a previous theorem, the big theta of f of n is the maximum of these two functions. Clearly the log n is larger than a constant function, so in conclusion, f of n is big theta of log n. Let me make an important observation here. The while loop in this algorithm always executes the same number of iterations for a given value of n. That is because the only way to exit the loop is when the subsequence under consideration is of size 1. So there's no such thing as a best case here. There's no way to exit the loop earlier than that. So as a result, what we just computed is not just the worst case time complexity, but it's also the same as the best case and the average case time complexity. Now, there are several variants of the binary search algorithm, and it's very likely that in one of your computer science courses, you have studied or you will study a variant of binary search that, at this point in time, will check if the target is equal to A sub m. And when that's the case, that algorithm will exit the while loop right away. With that variant of binary search, the best case and the worst case will be different. But as it is, our algorithm has only one time complexity, as was the case for the find max algorithm we discussed earlier. Now let's turn our attention to another algorithm that we studied before, namely the bubble sort algorithm, which solves the following problem. Now here is a description of the input and output of this algorithm, and here is its pseudocode. Make sure to stop the video and study this pseudocode again if you don't remember it that well. Now, let's perform the time complexity analysis of this algorithm. Remember that the first step is always to pick the type of primitive operations that we're going to count. Now, this algorithm is basically a nested for loop where the body of the inner loop contains a comparison and a swap operation. Remember that a swap can be implemented easily with a temporary variable using 3 assignment statements. So this is usually a constant number of assignment statements. We have a comparison here, and of course the overhead for the 2 loops is 1 comparison and 1 assignment statements for each loop iteration. So, should we choose assignment statements or comparisons? Well, in this case, I'm going to choose the comparisons. One reason for that is that it makes the analysis simpler. Notice that for every single iteration of the inner loop, this comparison is executed. On the other hand, the swap operation, which contains again 3 assignments, may not be executed when this comparison is, or this Boolean expression is false. So it's much easier to perform the analysis on the comparison in this case. I'll let you study on your own what happens if you chose the assignment statements as the primitive operations. Now, the next step is to determine the time complexity of the algorithm by counting the number of comparisons that it executes for a given input of size n. As usual, let f of n denote the time complexity of the algorithm for an input of size n. So f of n denotes the total number of comparisons executed by the algorithm. Let's count the comparisons on this line. When p is equal to 1, that is during the first execution of the outer loop, I goes from 0 to n minus 1 minus 1, which is n minus 2. Since we start at 0, that means the inner body is executed n minus 1 times, and therefore the number of comparisons in this first iteration is also n minus 1. When p is equal to 2, I goes from 0 to n minus 3. Therefore we have n minus 2 executions of the inner loop, and therefore also n minus 1 comparisons. Now, p keeps increasing by 1, therefore the number of comparisons keep decreasing by 1 as well until we reach the last iteration where p is equal to n minus 1. Now in this case, I goes from 0 to n minus 1, which is 1. 1 minus 1 is 0. So I goes from 0 to 0, which amounts to 1 execution of the inner loop, and therefore 1 comparison in the last iteration. So in conclusion then, f of n, which is the total number of comparisons, is the sum 1 plus 2 plus ... plus n minus 1. Now this expression for f of n is a little bit complicated, but fortunately we saw it before. This is nothing but the sum of the first n minus 1 integers starting at 1. And we know from a previous theorem that this sum is big theta of n minus 1 squared. So therefore f of n is big theta of this expression, which still looks a little bit complicated, so let's rewrite it. We of course know that n minus 1 squared is equal to this polynomial of degree 2. Every polynomial of degree 2 is dominated by its largest power of n, and therefore this function here is big theta of n squared. And as a final result, then f of n is also big theta of n squared. Now let me conclude this lecture by giving you a few exercises to work on at home. First, redo this analysis taking into account not just these comparisons, but also the comparisons that are built into the two for loops here, and see what result you get. Second, redo this time complexity analysis using not the comparisons, but the assignment statements contained in the swap operation here as well as in the loops, and see what final result you get and compare it to this one again. Now the third idea I have for you to work on is to look at other variations of bubble sort. In particular, you'll find that in some implementation or some variations of bubble sort, the best case time complexity is as low as big theta of n. Now, in those variants, the worst case and average case are still going to be n squared. But if you have time, you can look those up and see how it's possible to improve the best case scenario. And fourth, as a last exercise, I want you to go back to the insertion sort algorithm that we studied earlier and to perform a time complexity analysis on that algorithm.